I am very excited about today's lesson. Today, we're going to be learning about the shapes of compounds, or the shapes of molecules, I should say. And this is really where we get to the so what. Like, so what, all the stuff that we've been learning? What is the actual point? Well, I'll tell you what the point is. The point is that so that we can start to understand the incredible, like truly unbelievable world of the microscopic, of the like absolute tiniest levels of our universe. And what the really jaw-dropping thing is that these atoms that we've been looking at come together by the thousands to create these tiny machines, these molecular machines. And I just wanted to show you a couple of these machines now. This is a machine that does DNA transcription. And I know this is not a biology class. It's basically just making some DNA. It's making a copy of DNA. But what I want you to know is that thousands of atoms make the machine that you're about to see right here. So I want you to really look at what's going on. Look at the complexity of what's happening here. Look at this part right here. Grabbing that strand. Look at this. Everything that you see right now is happening due to little chemical reactions that are just driving themselves. This machine, it doesn't have a brain, right? It doesn't have a computer. This is made from atoms that are undergoing chemical reactions that change their shape and give it this ability to do this really incredible thing. This is a molecular machine. I find this just absolutely incredible. Let's look at one other one that I always found kind of funny. This is another molecular machine. Thousands of atoms come together to make a machine that literally walks, things within a cell. It just walks things around to get things where they need to go. So let's look at this. Look at this. That is a motor protein that's formed from thousands of atoms that undergo these little chemical reactions that literally make this little walking thing. It's just like, I find it unbelievable. So, what we're going to learn today is the really basic idea that shape matters. Shape matters a whole lot. We're not going to look at anything nearly as complex as this. This is thousands of atoms coming together. But we can start learning about what happens when just a few atoms come together, and you're going to see the complexity and the incredible things that can happen in terms of the shapes that are formed. So let's go ahead and get started. We're going to be learning about something called VSEPR theory, and it lets us predict the shapes of covalently bonded molecules. So right away, I want you to be aware that we're talking about covalent bonds, which means that we're going to be dealing with sharing of electrons. The key thing to remember with VSEPR theory is that electron pairs repel other electron pairs. And this should be somewhat familiar to you already. We already have talked at length about how like charges, let's say this is an electron with a negative charge, repel like charges, right? So like charges repel, opposite charges attract. If we're talking about electrons, we're saying that the electron pairs are going to repel each other. So you can kind of have this picture in your mind of electrons repelling or pushing away from each other. That's kind of the basis of what we're going to be looking at today. Because they repel, they force molecules into certain shapes because they want to get as far away from each other as they can. And we can predict the shape of a molecule by counting the number of electron concentration areas. We're going to talk a lot more about what that means around the central atom. So this phrase right here is going to be the most difficult to understand right now. What I want you to know is that just using the idea that electron pairs want to get as far away from each other as possible, we're going to be able to predict the shapes of molecules. And so it just notes that you have to be able to draw Lewis dot structures for this, but we've already been practicing that, so you should be pretty well equipped to do this. So what is VSEPR theory? What does it stand for? First of all, it's this very clunky acronym that stands for valence shell electron pair repulsion. So that's a fun mouthful. Valence shell electron pair repulsion theory tells us that areas of a molecule that have higher concentration of electrons will repel each other, meaning areas around areas of molecule that have electrons or higher concentration of electrons want to push away from each other, right? And that's going to affect the shape of the molecule. For example, we know already that if we're looking at this covalent bond, we know that because of this tug of war of electrons that happens, where is there going to be a higher concentration of electrons, or where is there going to be an area of electron density? Hopefully you look at this and say, well, right here, right? This is where the electrons are spending most of their time because they're being tugged by both of the atoms. And that's exactly right. So the area between the atoms in a covalent bond is where you get these electron areas, these areas of electron density. And it's going to tell us that right now. So just as we explained, we see that the electrons mostly are spending time here in the actual covalent bond, right, in the area between the two atoms. And so this is sort of a more typical picture that you see. Usually when we draw covalent bonds, or when you see molecular models of covalent bonds, they sort of draw the atoms like this, as just these spheres, with the area of high electron density in between as sort of a stick, or in this case, it's like a strip. And so what we want to show you now is that let's imagine we have an atom that's bonded to two other atoms, and it's covalently bonded with areas of high electron density right here and here, right in between both of the atoms. And so what the idea is that they want these areas of electron density want to be as far away from each other as possible. So what's going to happen if I, for example, swing this red atom over this way? Let's see what happens. So this electron density area repels this electron density area, right? So let's see. Let's do it this way. Let me try to catch the blue. Yep, sure enough, no matter what I do to the red one, these electron areas are going to repel each other, forcing the atoms that it's connected to be as far apart as possible. In this case, it's 180 degrees, right? Which is how you could kind of describe a line. What do you think? I want you to imagine for a second. What kind of spacing do you think is going to happen when we add a third atom? When I press play, these electron areas are going to repel each other. What kind of shape do you think might happen? They sort of form this triangle shape with 120 degrees between each atom. Now that doesn't mean that angle doesn't change, right? If I drag this red atom over there, for some reason it'll change momentarily, but it's going to slowly work its way back to its own equilibrium where they're as far away from each other as possible because these electron areas are repelling each other. And so it turns out that farthest distance that they can be from each other is 120 degrees. What do you think is going to happen when we add a fourth atom? I want you to take a moment and think about what do you think the spacing will look like if we add a fourth atom. Did you guess that they would have 90 degrees between them? That is actually not correct. So if you think about 2 dimensions only, right? If we think about us looking at something drawn on a flat piece of paper, or in this case on a flat screen, it's easy to sort of think, oh yeah, they're going to have 90 degrees, there'll be right angles between. But if we move into 3-dimensional space, there's another configuration that's possible that can move them further than 90 degrees from each other. And that is this shape right here, 109.5 degrees between each of the atoms. And you can see that we've moved into a 3-dimensional shape now. So let's look and see if we can predict a few molecular structures. Let's start with carbon dioxide. So, right, this is a covalent molecule. So we're going to say the first element, then the second element, adding the "ide" suffix and the di prefix. Let me just write that out for us. We've had a lot of practice writing these. So we would write carbon and we would write di because we have two oxygens, oxide. Okay? And so what we need to do first is see how can we predict what shape it's going to make just by knowing the formula. Or we know we have one carbon oxygen and two oxygen atoms. I'm sorry, we know we have one carbon atom and two oxygen atoms. I've made this poor little molecule go really wild here. So let's draw the Lewis structure. If we were going to draw carbon, I'm going to draw it up here for a moment. If we're going to draw carbon, we know that carbon has 4 valence electrons. I'm going to draw them like this. We know that oxygen has 6 valence electrons. By now, hopefully you're starting to be able to know that that's going to end up with 2 unpaired electrons and 2 lone pairs. Let's draw one more here. Oxygen. And so let's start drawing some bonds, right? Let me choose a different color to show this. So right away, I know that carbon wants to make 4 bonds. Each oxygen only wants to make 2. So it turns out there's a pretty simple fix to that. We can bond these 2 atoms and, these 2 electrons and these 2 electrons. And let's do the same over here. This electron and this electron. Well, this is quite ugly, so let's see if we can make this look a little prettier. So here's going to be our Lewis dot structure. Carbon double bonded to an oxygen, double bonded to an oxygen, and we should have 2 lone pairs left around each oxygen atom. Let's just double check that this makes sense. Carbon wants to form 4 bonds and wants to have 8 electrons total. So each of these lines represents 2 electrons, so 2, 4, 6, 8. So carbon is very happy. Oxygen also wants to have 8 electrons around it, so 2, 4, 6, 8, and 2, 4, 6, 8. So all 3 of these atoms have satisfied their octet rule. Let's erase this and see if we've done well. So yeah, this is exactly what we drew, right? We said that the Lewis dot structure would look like this. The central carbon atom has 2 double bonds. And what happens is each of those bonds is shown in this 3D molecule as a yellow ball. Let's just turn this here. So you see each of these little yellow balls represents a bond. So if we look here, this red sphere here represents this oxygen atom. And it has 2 bonds, so that's represented by 2 of these yellow balls. Then we have our carbon atom, which is typically represented in black. And then we should have 2 more bonds in between the carbon and the next oxygen. Let's rotate this. So yep, sure enough, there it is. So there are 2 more bonds, and then finally another oxygen atom at the end. Now we're missing our lone pairs, so let's see what that looks like. Here we go. So now it's pointing out the lone pairs, and we see that each oxygen atom should have 2 lone pairs. Now, I want to show you something that I find pretty amazing. It turns out that when we're thinking about double bonds, it's useful to think about them in this way as sort of these just 2 little, yellow balls connecting them, but it's a little bit more complex and kind of amazing. So if we're looking at, I don't want anyone to get scared here. It's going to look really wild here at first. If we're looking at CO2, this black atom here represents carbon. Each of these pink atoms represents oxygen. And what's really amazing is that a double bond is actually formed between the p orbitals of the oxygen and the carbon atom. And so just as a quick reminder, if I pull out here our structure that we had looked at before, these, hopefully you can remember that this white ball represents an s orbital, and then these are the 3 p orbitals that we've looked at great length, right? The purple, each color represents a p orbital. Well, here I want you to kind of see that what's being represented is that we had some p orbitals. These purple ones are sort of represented by this bond right here. that overlaps with another p orbital. And so it creates this area of electron density between those two p orbitals. I know that that's really hard to understand and imagine right now. Right now, I just want you to get used to the really amazing fact that this is really what a double bond looks like. It looks like a bond right between the two atoms, and then it's actually it's like a sandwich. The double bond is like a sandwich that goes above and below that bond. It looks kind of like this would be a triple bond, but it's not. This is just a double bond. Both of these represent one double bond, and then this is the single bond. This is the first bond, this is the second bond. And then that same thing happens with the other oxygen atom, but now we had to use the other p orbitals, right? In this case, they're the same color, but I want you to just imagine that just as we looked at when we were looking at our electron orbitals, we have a p orbital here that might have formed a double bond, and then we have another p orbital right here that could have formed another double bond. And so you see that they're perpendicular to each other, and we do see that these double bonds, so here's one double bond, here's another double bond, and look how amazing that shape is. Look how amazing that shape is. And then over here, I've represented the lone pairs of the oxygen atoms using these sort of pink wedges. Now I want you to just remember that these aren't atoms here. They're just showing where the lone pairs of electrons are hanging around. Okay? So I've sort of shown it like that. I do want you to know that it's probably a little bit more realistic to sort of picture this as not even having these electrons there, right? Because really those electrons are not going to add mass. They're very, 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 very tiny compared to the atom. And so you can kind of picture the molecule as being without all these extra electrons. Okay? So that's maybe more of what the molecule might look like. But that said, I do still want to make sure that we keep in mind that there are lone pairs on each of these oxygen atoms. So I'm going to put them back on just for the sake of us remembering that. Very important information. And so again, let's just go back to this simpler model, maybe not as reflective of what is actually happening, but it's just easier to imagine this way. This is our simpler model of carbon dioxide. And so what we can do is imagine that this carbon atom has two areas of electron concentration around it. One between each of its oxygen atoms that it's bonded to, right? One more time, I just want to show you that if we look at it this way, it looks a lot more complex, right? But we are just saying that there are two areas of electron concentration around the carbon atom, one on this side between the carbon atom and the oxygen atom, and one on this other side between the carbon atom and this oxygen atom, right? There's just electron density on either side. It just looks kind of complex when we do it this way, but we can just imagine it like this. And so this forms a linear shape, right? These atoms are just all lined up. We saw that in the model that I showed you. We can rotate it around and just see that they're lined up sort of in a line. This is called a space-filling model. And each of the outer atoms are 180 degrees apart from each other. So the oxygen atoms are 180 degrees apart. Let's look at another molecule. Let's talk now about the ion NO3 negative or nitrate. We have not talked about what is called polyatomic ions yet, but we will soon. It says let's try drawing the Lewis dot structure on our own, but I'm actually going to just continue for the sake of time. This is what a Lewis dot structure of the nitrate ion would look like. Note that it's got one extra electron, and so that's why it has this negative sign right here. This ion formed by this polyatomic ion has one extra electron. And so what that looks like, if we actually show it in our geometric model, if we want to see what shape it makes this sort of flat triangular shape. Now notice that we've got a double bond between the nitrogen and one of the oxygen atoms, and then single bonds between nitrogen and the other two oxygen atoms. Just for fun, I'd love to show you again what the model would look like if we're showing that double bond in a little bit more a realistic way, showing it as above and below. So this is kind of our model here, right? We see that it's got a double bond. Let me see if I can move this out of the way. We see we've got the bond between the nitrogen and oxygen here. Actually, all of these outside ones are oxygen. I just ran out of pink atoms. So we've got a bond between the nitrogen in the center and the oxygen. That's a double bond represented by one bond in between the atoms and one bond on top and bottom. And so we see that if we look at the shape that the atoms take, right, the atoms here are this nitrogen atom and then the 3 oxygen atoms, it makes this sort of flat triangle shape. It's a little more complex, right? There's all kinds of other things going on. We've got all these lone pairs on the oxygens. So the oxygens that have a single bond have 3 lone pairs that take up a bunch of space, right? Even if they aren't big and heavy like the atoms, they do take up space. And they all want to get as far away from each other as possible. But the actual atoms form this sort of triangular shape here that is just more simplified when we look at it this way, right? It's a little bit easier to see the actual shape. I just wanted you to see what it might look like. And here it's showing now all the lone pairs as well. So when we look around, we will find that there are 3 areas of electron concentration around the nitrogen atom. Now I want you to look at this Lewis structure as well and see that it's kind of easy to see that there's 1, 2, 3 areas of electron concentration. Right? Now they're not all the same. One is a double bond and each of the others is single bonds. But for the purposes of what we're doing here, we just want to know that there are 3 areas of electron concentration. And so what we need to understand and see here is that these areas are going to repel each other and force the oxygen atoms apart. That's why they made this shape. This shape is called trigonal planar. Trigonal planar. Now, it's not so hard to remember if you remember that tri is the prefix for 3. So we have these 3 points to our sort of triangle, trigonal. And then planar, just think of that as like a flat plane, a flat plane. That's what the planar is supposed to make us think of, that it's just sort of like this 2-dimensional thing almost. It's flat, trigonal planar. And we see that if we look at it from this angle, we can see that it's pretty flat. They're all on the same plane. Look at it from this one, we can see all 3 different points of that triangle. And this is the space-filling model of that molecule. We should keep in mind that the bond angle in a trigonal planar molecule is 120 degrees. Let's now look at SO2. So SO2, let's just look at the Lewis structure. Hopefully, or you could even take a moment and try to draw it if you like. But for the sake of time, we're just going to say that SO2 is happiest when we have a sulfur atom double bonded to one of the oxygen atoms and single bonded to the other oxygen atom. Okay? Note that the sulfur has a lone pair on it. Okay? So let's look and see what shape that's going to make. So the lone pair on the central atom is shown in yellow, and the bonding pairs are shown in black. So let's look at this. So this is representing the lone pair on the sulfur atom, and these are the bonding pairs. Okay, note that on one of them, it has 2 bonding pairs. The other one has just the 1 bonding pair. That's the double bond and the single bond. And we know that what we need to understand is that the lone pair is going to repel the bonding pairs as though they were an imaginary oxygen atom. So the lone pair is going to repel these as well. Even though there's no atom over here, the lone pair is still going to repel these other electron concentration areas. And just to show you what that might look like with our molecular models, let me just bring this over here again. So here we have our molecular model of this. I've represented the lone pair on the sulfur atom with this purple sort of lone pair thing, this purple little cloud. And one of the oxygens has 3 lone pairs around it. And the other oxygen has just 2 lone pairs because it's double bonded to that sulfur atom. And I just want to point out that if we look at the atoms themselves, we do see that they form sort of this bent shape, right? Almost like it's part of, I don't know, like part of a box or something, but they're 120 degrees apart with just a little electron cloud up here. Again, it might be sort of easier to imagine it as like this, right? But it is important that we know that even though we can't, those electrons are not going to be taking up or don't have a bunch of mass, they still take up space. And so I'm going to keep that lone pair on there for that reason. And so in the case of SO2, there are still 3 areas of electron concentration, even though on one of them, it's just a lone pair. So 2 of those areas are one between each of the oxygen atoms that it's bonded to, and the other area is the lone pair. And so it's going to have the same repulsion that we saw in the previous example, only that now on one side of that triangle, there's nothing, right? It's just an empty space. This is called a molecule with a bent structure. It's bent. It just looks like it just looks like it has sort of this bent shape. I don't know how else to say it. And if we do away with the lone pairs, then we can see that bent shape even more clearly. Again, this is the sulfur atom, and then we have the 2 oxygen atoms. So this is a bent shape. And they've got about 120 degrees between them. Here's the space filling model for that. Now let's look at another one. Let's look at methane now. So methane is a Lewis structure showing carbon with 4 hydrogen atoms bonded to it. And as we saw before, these 4 bonds are all going to repel each other, right? And so let me just put together my little methane molecule that's going to look a lot more this time like the one that it's showing you, because there are no double bonds present. So I don't have to have my amazing double bond demo for you. And so if we were making this with a molecular model, it would look like this. Here's my methane model. These little white balls at the end represent the hydrogen atoms, and the center one represents the carbon, with the electron concentration areas between them as the bonds, right? The covalent bonds. So take a look at this shape. So we know they're going to repel each other and make this amazing shape here. And we have that 109.5 degrees between each of these atoms, between each of the hydrogen atoms. And this molecular shape is called tetrahedral. Say that 5 times fast. Tetrahedral. I'm not even going to try. I can't. This is our tetrahedral shape. It's got 4 electron areas around it. That makes a tetrahedral shape. But things can get a little bit more complicated when you start to have a tetrahedral shape, but not all of them are bonded. So let's look at, first here's our space filling model of our methane, CH4. Now let's look at what happens if one of those hydrogen bonds is replaced with just a lone pair. So in the case of nitrogen, for example, that only wants to form 3 bonds and have its lone pair, this is what would happen. We would have sort of our ghost hydrogen, right? It has the same shape if we count the lone pair, right? So if we counted the lone pair, it would have a tetrahedral shape. But really what ends up happening is we get a shape that looks like this. It's kind of like a pyramid. It's called trigonal pyramidal. So instead of being trigonal planar, as in flat, it's trigonal pyramidal. And let me just show you what this would look like in my molecular structure. So if it had that lone pair on it, it would look like this. But what I want you to know is that what we would really, in terms of where the mass is, these electrons do repel things, but they're not massive, right? And so this is really the shape that the molecule is going to take, right? We have this kind of interesting shape that almost looks like the bottom, like a pyramid. All right, and that's why it's called trigonal pyramidal. So let's just look at the space filling model one more time. So we see we have these three atoms that are closer to each other on one side, because on the other side, we just have to remember that it's got that lone pair, and that's why it's sort of forcing those three down so that they're not flat, but actually forming a sort of pyramid shape. So that's an example of NH3 or ammonia. And now let's look at our last molecule here. Thank you all for sticking with me all this time. Let's look at our molecule of water. So water is definitely very important to us. Here's our Lewis dot structure. But what shape is this actually going to make? It turns out it's also going to make a bent shape, but this bent shape is going to have a 109.5 degrees between the atoms because it's coming from a tetrahedral formation, right? Except that two of these electron concentration areas that are part of the tetrahedral are not connected to any atoms, right? So we have sort of these ghost atoms. And let me just show you the molecular structure as well, if I was doing it with a model kit. So here's this. And if we take off the lone pairs, we can really see what shape the actual atoms make, which is this, right? So here's our shape of water. This is representing the oxygen atom. These are representing the hydrogen atoms. This is our shape of water. We just have to know that the reason that these are being pushed down here instead of being straight is because oxygen actually has these two lone pairs on it, right? And so that's what makes it have this bent shape. So these are our two lone pairs right here. And so this is, again, this is called our bent shape, but it has a bond angle of 109.5. The other time we saw one with a bond angle of 120 degrees because it was a trigonal planar geometry with one lone pair. Well, this is a tetrahedral geometry with two lone pairs. And so we have different bond angles, even though we have a similar shape. So if we look at our space filling model, here's our model for water. That's a water molecule. Last sort of section that I want to cover is how do we draw these when we don't have these amazing molecular shapes, right? These are very beautiful models. I cannot draw anything remotely like this. So how would we draw this? How would we draw a tetrahedral shape? And so what I want you all to see is that we're going to just have to sort of use our imagination and understand what certain symbols mean. If we want to draw something going straight up and down, almost like it's flat on the paper, we just draw a straight line, right? Just like we've been doing. So that is familiar to you. So these bonds are shown by just regular lines. But if we want to show this hydrogen atom that's sort of coming out of the page toward us or out of the screen toward us, we show a wedge shape like this. So a wedge shape just means it's coming out of the page toward us. We just have to know that that's what it means. And if we want to draw something that's sort of behind these atoms or like going back into the screen, we draw it as a little dashed line. Okay, and so if I was going to draw this to the side here, well, I think it's going to draw it for me in a moment. Let me erase this so we can see how the pros do it. So here is our wedge and dash drawing. The dotted line is behind the carbon atom. The wedge is in front of the carbon atom. Maybe I'll just draw it. I do actually want to just draw it really quick. So this is, without these beautiful shapes, it would look like this. I would draw this and say, okay, it's tetrahedral. So if it was trigonal planar, which it's not in this case, right? But let's say, for example, that I wanted to double bond this to an oxygen. This would be a trigonal planar. It is flat. And so I don't have to do any fancy wedges and dash lines. It's all flat. I just imagine that it's flat on the screen. But if I wanted to draw a tetrahedral shape, I can't draw that flat on the screen because it's not flat, it's 3D. And so I would say, oh, one of my hydrogen atoms is going to come out of the page towards us. and the other one is like behind this carbon, and so I'm going to draw it with a dashed line. And so that's just my way of showing the tetrahedral shape, right? Even though it's like really challenging to draw that, this is me showing that tetrahedral shape. So in this tutorial, you learned the following. Electron pairs repel other electron pairs. Because they repel, electron pairs force molecules into certain shapes. And the number of electron concentration areas around the central atom determines the shape of the molecule. And I just want to do a very, very quick sort of like review of what we learned, almost to give you a little bit of a cheat sheet here. If you have an atom that has either two double bonds, if you have some atom, I'm just going to put atom X, that either has two double bonds on either side of it with some other atoms. I'm just going to draw a ball on this end. Or if you have a triple bond on one side, it might have a single bond over here, it might have a lone pair. These are generally, not always, but generally going to be linear because they have two areas of electron concentration around them, right? It looks different depending on the way, but they each have two areas of electron concentration around them. And so that's going to be linear. If you have some atom with three areas around it, right? So let's do an atom with just three areas, only three. Let's say, I don't know, let's say it's a bond and then maybe a double bond here and then maybe a single bond. Why, you might ask yourself, why didn't I do them all single bonds? Because remember that they want to have 8 electrons around them, right? Atoms want to have 8 electrons around them. And so if I just did a single bond here, this atom wouldn't be happy. It would only have 2, 4, 6 electrons around it. So I'm going to do a double bond here just to represent this. Well, this has got 3 electron areas around it. And this is generally going to form either a trigonal planar or if one of them is a lone pair, if you have one lone pair, a bent with 120 degrees between the atoms. Right? So imagine if one of these was gone because it was a lone pair, the lone pair still repels, so it's still going to form this shape, but we'd only have these 2 atoms on each side. And then if we have 4 areas of electron concentration, now you might draw this like this. You might draw it like this. But you have to know that this is actually better represented. It's better represented if you draw it like this. Our tetrahedral shape, right? And so you're going to have several things. If you have atoms attached to all of them, right? If you have atoms on each of these 4 electron areas, right? Let me just sort of highlight these are the 4 electron areas here. 1, 2, 3, 4. If you have atoms bonded to all of them, you're going to end up with a tetrahedral. If you have one lone pair, let's replace one of these with a lone pair, you would just end up with your trigonal pyramidal, right? That lone pair is still going to repel them. It's just not going to be involved in terms of the shape of the molecule because it's just electrons. It doesn't really have mass compared to when we're looking at atoms. And so you could also have trigonal pyramidal. And if you replace them with 2 lone pairs, you're going to end up with a bent shape, but with 109.5 degrees between them, because that's the angle between tetrahedral formation, tetrahedral shape. Let me just sort of add in here the lone pair info because that's probably going to be useful. So tetrahedral is connected to 4 atoms. Trigonal pyramidal is if you have one lone pair. I'm just going to write LP. Bent is going to be if you have 2 lone pairs. And up here, our bent here is if you have 1 lone pair, right? This is if you have 0 lone pairs. This is if you have 0 lone pairs.